Basic Vibration Analyst, Vibration Analysis, what is resonance and understanding vibration behavior and its effects. Introduction to the importance of vibration analysis. Vibration analysis is a critical technique in mechanical and structural engineering used to monitor, diagnose, and prevent equipment failures. It involves studying oscillatory motions of components to identify abnormalities that could lead to breakdowns or inefficiencies. By analyzing vibration patterns, engineers can detect misalignments, imbalance, bearing faults, and resonance conditions before they escalate into costly failures. This proactive approach enhances reliability, reduces downtime, and ensures safety in industries such as manufacturing, aerospace, and automotive. Vibration analysis also supports predictive maintenance strategies, allowing organizations to schedule repairs based on actual equipment condition rather than fixed intervals, thereby optimizing operational costs and extending asset life. Basic concepts of vibration, frequency, amplitude, and damping. Understanding vibration requires familiarity with key parameters, frequency, amplitude, and damping. Frequency refers to how often a system oscillates per unit time, typically measured in hertz or hertz. Amplitude indicates the magnitude of displacement from the equilibrium position, reflecting the intensity of vibration. Damping is the mechanism that dissipates energy, reducing vibration over time. These parameters interact to define the dynamic behavior of mechanical systems. For instance, high-amplitude vibrations can indicate severe imbalance, while insufficient damping may lead to prolonged oscillations. Engineers use these concepts to model systems, predict responses, and design components that minimize harmful vibrations. Types of vibration: free versus forced vibration. Vibrations can be categorized as free or forced. Free vibration occurs when a system oscillates without continuous external force after an initial disturbance, such as a plucked guitar string. Its frequency depends on the system's natural properties like mass and stiffness. Forced vibration, on the other hand, happens when an external periodic force drives the system, such as machinery subjected to rotating imbalance. Forced vibrations can become problematic when the driving frequency matches the system's natural frequency, leading to resonance. Understanding these types helps analysts predict system behavior under different operating conditions and design strategies to mitigate risks. What is resonance? Definition and significance. Explanation of resonance. Definition and significance. Resonance occurs when the frequency of an external force matches the natural frequency of a system. This causes large amplitude vibrations, which can lead to damage or failure. Key points of resonance: every system has a natural frequency. External periodic forces, such as rotating machinery imbalance, can excite resonance. Damping reduces resonance effects but cannot eliminate them completely. Resonance is a phenomenon where a system experiences a dramatic increase in vibration amplitude when the frequency of an external force matches its natural frequency. This condition can lead to catastrophic failures if not properly managed. Resonance amplifies energy transfer, causing components to oscillate excessively, which may result in fatigue, cracks, or complete structural collapse. Engineers must identify and avoid resonance during design and operation by adjusting system parameters or introducing damping. Recognizing resonance is essential for maintaining equipment integrity and ensuring operational safety across industries. Here's the resonance and resonance phenomenon diagram. Left diagram shows a spring mass system with external force frequency matching natural frequency will lead to large vibrations. Right diagram is an amplitude versus frequency curve with a peak at natural frequency, resonance, and note on damping reducing amplitude. Natural frequency and excitation. Every mechanical system has a natural frequency determined by its mass and stiffness. When an external force excites the system at this frequency, resonance occurs. The energy input aligns with the system's inherent oscillatory pattern, causing amplitude to spike. Mathematically, resonance is described by the equation of motion for a damped harmonic oscillator, where the response amplitude becomes maximal at the natural frequency. Engineers use modal analysis and frequency response functions to predict resonance conditions and design components that avoid critical frequencies during operation. Structural and mechanical failures, real-world examples of resonance. Resonance has caused numerous engineering disasters. A famous example is the Tacoma Narrows Bridge collapse in 1940, where wind-induced oscillations matched the bridge's natural frequency, leading to catastrophic failure. In rotating machinery, resonance can occur when operating speeds coincide with critical speeds, causing excessive vibration and bearing damage. Turbine blades, aircraft wings, and engine components are also susceptible to resonance, which can result in fatigue and fracture. These cases highlight the importance of identifying resonance during design and implementing preventive measures to ensure safety and reliability. Resonance curve, amplitude versus frequency relationship. The resonance curve illustrates how vibration amplitude varies with excitation frequency. At low frequencies, amplitude remains small, but as the frequency approaches the system's natural frequency, amplitude rises sharply, peaking at resonance. Beyond this point, amplitude decreases due to damping effects. This curve helps engineers visualize the critical frequency range and design systems to operate outside resonance zones. By analyzing resonance curves, analysts can predict potential issues and implement corrective actions such as altering stiffness, mass, or adding damping to shift the natural frequency away from operational ranges. Factors affecting resonance, mass, stiffness, and damping. Resonance behavior depends on system properties such as mass, stiffness, and damping. Increasing mass lowers natural frequency, while increasing stiffness raises it. Damping reduces amplitude at resonance, mitigating harmful effects. Engineers manipulate these parameters during design to avoid resonance within operational ranges. For example, adding dampers to automotive suspensions or adjusting blade stiffness in turbines helps control resonance. Understanding these factors enables analysts to predict resonance conditions and implement effective preventive measures. Consequences and prevention, impact and mitigation strategies. Uncontrolled resonance can lead to severe consequences, including structural damage, component fatigue, and catastrophic failure. Preventive strategies include designing systems to operate away from natural frequencies, adding damping elements, and conducting modal analysis during design. Regular vibration monitoring and predictive maintenance help detect resonance early, allowing corrective actions before damage occurs. Implementing these measures ensures equipment reliability, safety, and cost efficiency. Let's summarize and key takeaways of resonance concepts. Resonance is a critical concept in vibration analysis, representing a condition where external excitation matches a system's natural frequency, causing amplified oscillations. Understanding its physics, consequences, and preventive strategies is essential for engineers and analysts. By applying vibration analysis techniques, industries can enhance reliability, prevent failures, and optimize maintenance practices. Awareness and proactive measures against resonance safeguard both equipment and human lives.